Integrity, as another classic security goal of cryptography, is the goal demanding that the correctness and completeness of information can be verified. Correctness of information means that every bit of that information is exactly the 0 bit or the 1 bit that's expected to be there, and completeness of information means that the information neither misses a single bit, nor does the information have a single additional bit that's not supposed to be there. The primary primitive with which cryptography can serve integrity-related purposes are cryptographic hash functions. Taking first a quick step back, a hash function is, as the name indicates, a function mapping elements of a certain input domain to elements of a certain output domain of hash values. In the example drawn on the slide, the hash function h maps the element x1 to the hash value h of x1 and maps x2 to the hash value h of x2. Additionally to just being a hash function is a function that is easy to compute and a function whose input domain is binary strings of arbitrary length and whose image domain of hash values is binary strings of a fixed length. Instead of just the 4 elements x1 to x4 listed, the input domain for the hash function h would thus contain many more elements and would actually be of an unbounded size. The image domain of hash values may very well just contain the 3 elements listed, however, as the image domain of a hash function is of a fixed and bounded size. In order for a hash function to be useful for cryptography as a tool to allow the verification of the correctness and completeness of information, a hash function would actually need to be injective and map inputs to unique hash values such that a hash value would uniquely identify the information. However, as the input domain to a hash function is much larger than the domain of hash values, this uniqueness of hash values is actually impossible for hash functions to realize, and instead of requiring the uniqueness of the hash values, one now requires that it must be merely difficult, not impossible, but difficult, to find different inputs that would be mapped to the same hash value. If that's the case for a hash function, then the hash function is called a collision-resistant hash function, and it's then the 2 properties of being one-way and collision-resistant that turns a hash function into a cryptographic hash function that can be used for integrity-related cryptographic purposes. It's now time to look at examples of real-world hash functions where we find that the 4 most commonly used hash functions are often either message digest 5, MD5, the secure hash algorithm 1, SHA-1, the secure hash algorithm 2, SHA-2, or the secure hash algorithm 3, SHA-3. MD5 is a hash function producing 128-bit hash values, and the hash value that MD5 calculates on the input fundamentals of cryptographic hash functions is the 128-bit hash value reading 6D7A and so forth when expressed as a hex string. SHA-1 produces 160-bit hash values, and the 160-bit hash value SHA-1 produces on the same input string is the hex string starting with 5EFF as shown on the slide. With SHA-2, the length of the hash value can be chosen to either be 224 bits, 256 bits, 384 bits, or 512 bits, and the 256-bit hash value of SHA-2 for again the same input is the hex string shown on the slide, starting with 41BF and so forth. Also, for SHA-3, the length of the hash value can be chosen, and the 512-bit hash value calculated by SHA-3 for, again, the same input is the hex string starting with 48CE as shown on the slide. The question left to answer is whether all of these hash functions are now indeed secure cryptographic hash functions and with the definition presented on the previous slide, the question is whether all of these hash functions are one-way functions and collision resistant. Interestingly enough, all of these 4 hash functions are up until today assumed, not proven, but assumed to be one-way functions. The story looks different with respect to the collision-resistant property. Message digest 5, the oldest hash function released back in 1992, has been assumed as of quite shortly after its release that collisions will be found one day, and indeed the first collision for MD5 was found in the year 2004, with nowadays collisions for MD5 being calculated within fractions of seconds on normal desktop computers. What is indicated on the slide for MD5 is that in order to calculate a colliding pair of inputs for MD5, roughly 2 to the power of 18 evaluations of MD5 need to take place, which is significantly lower than what would be expected of collision-resistant hash functions. From this, it's clear that MD5 is not a secure hash function and should not be used for integrity-related cryptographic purposes. For SHA-1, which was released in 1995, it was rumored as of the early 2000s that collisions may be found one day, and indeed, back in 2017, researchers at Google fabricated a pair of PDFs that are very clearly very different PDFs, but with both PDFs having the same SHA-1 hash value and thus breaking the collision resistance property of SHA-1. For Google, the fabrication of the 2 PDFs took roughly 2 to the power of 60 evaluations of SHA-1, which again is significantly lower than what would be expected of collision-resistant hash functions, and thus rendering also SHA-1 insecure for integrity-related cryptographic purposes. On the other hand, both SHA-2 and SHA-3 are up until today assumed to be secure cryptographic hash functions, secure for all the possible lengths of hash values they can calculate. All of this leads to the final conclusion that MD5 and SHA-1 are not secure cryptographic hash functions that should be used at most for legacy purposes, and that for new systems either SHA-2 or SHA-3 must be used for integrity-related cryptographic purposes.